Thanks for your patience. Let's go to the end of the talk. No, I'm kidding. So no, first, I need to thank my sponsor who makes it possible for me to work on the project. And also, yeah, I can give you the agenda. So I will start by giving you some context that motivated me to work on this project. Then I will show you a demo on how it works. And then I will summarize the main design decisions I've made. So, context. Let's talk about architecture, or structure, if you prefer. One way of designing applications is to make monolith, where the entire system fits into a single application. And the benefits are that it's simple to understand, but it has some drawbacks, and it enforces some rigidity. Like the whole team has to work on the same code base with the same set of libraries. If you want to migrate to a new version of the library, you have to upgrade the whole project, and this has a high cost. It's harder to scale as well because you have to duplicate the entire application. You cannot just identify the bottleneck and scale that part out. So what is the answer to these problems? The distributed architecture, right? And by distributed, I mean in the general sense, like web application is distributed because you have just more than one node. You have a backend and a front end that communicate together. And more generally, the backend itself can be made of several nodes that communicate together. And now the situation is reversed. Instead of rigidity, we get flexibility. Each node can be worked on by an independent team using the technology of their choice. They can make their own experiments. And also you can now just scale out the critical nodes of the application of the system. But it also has some drawbacks. So instead of simplicity, we now have complexity. And essentially because all these nodes have to communicate together, and this is something that is not necessary in the monolith world. And also, we pretend that the teams can work independently on each other on each node, but in practice, all the work has to be coordinated because there are interdependencies between the nodes. But in this talk, I will only focus on the first problem. And Noel Markham said someone that about this specific problem of communicating between programs. So Noel Markham said that when you turn from a monolith to a microservice, you effectively trade a function from A to B into a function from A to future of either HTTP error, either JSON deserialization error B, right? And this is because, indeed, the network can fail, your HTTP request might be invalid, and the JSON response you get from the server might not match the format you are expecting. So this introduces more points of failure. So that's what Noel Markham said, but how does it look like in practice, right? What do we do in practice? Do we really suffer from this problem or not? So I want to try to give an overview of the existing techniques that exist to communicate between programs, and I will start with a very old technique that was invented more than 20 years ago, and which is actually built into the JVM, and that greatly simplifies the model of programming. Do you have any idea of which one I'm talking about? Yes, Java RMI, which gives you a very, very nice, or maybe not, programming model, where you can hold a reference on a local JVM, a reference to a remote object, and then when you invoke an operation on this local object, the JVM takes care of serializing the arguments, calling the corresponding method on the remote object, on the remote JVM, and then deserializing the response. So, problem solved. Remote invocation is back an A to B function, right? that's actually not that bad. And another benefit of Java RMI is that you get tooling assistance, you get compilation time errors if you try to invoke a method with an invalid argument, right? But who has worked with Java RMI? Not a lot, okay. And did you find any issue with this technique? Okay. So the one I've listed is that first it's blocking, and it's not efficiently using the computing resources of your machines. There is no streaming support, so it was invented like more than 20 years ago, and there was no real-time notifications at that time, so streaming was not a concern. And last but not least, network failures surface as runtime exceptions. And more generally, you can have lots of runtime exceptions in situations that you would not expect, just because actually the programming model is dangerous, because it tries to give you the ability to work with remote objects as if they were local, right? And in practice, doing this in a transparent way is impossible to achieve. So giving the illusion of transparency is dangerous. So how did we fix this problem? Because, I mean, since that time, we have invented better solutions. And there is a library in Scala that is popular to work with distributed systems, and that does not suffer from this very problem. Do you know which one I'm talking about? Akka, yes. So with Akka, the programming model looks like the following. You have a reference to a local actor, and you can, to invoke an operation on the actor, you have to use the ask pattern, and which lets you send a message to the remote actor, and you have to just pass it the reference it will reply to. And eventually you get a future of B containing your result. And so the benefits of Akka is that it's non-blocking, it's efficient, it supports streaming with Akka streams and reactive streams, which has great properties. And also it achieves distribution transparency without being dangerous, because it lowers the guarantees you get when you invoke, when you make invocations to local actors. So it gives you less guarantees than if you were just invoking a function. So this is Akka, the benefits, and now the limitations. So still the programming model is a little bit more cumbersome to use than just invoking a function, mostly because everything returns unit in Akka. So you might end up having to write a lot of plumbing code to get back a future of B. And this point also applied to Java RMI. So when you build a system with Akka, all the nodes of the system have to speak the Akka protocol, and currently I think it's only implemented on the JVM, so it does not give a lot of flexibility for your clients to use your system. So it's definitely not something that you want to use when you want to expose a public API, right? So what do we use to expose a public API? Okay. Lots of different options, but the one I wanted to show now is HTTP. And so now the programming model looks like the following. You build an HTTP request, you have to serialize your arguments, you have to check that the server understood what you requested, and then you have to check that you understand what the server replied to you. And what you get is more flexibility, because client and server are completely decoupled in the sense that they can use whatever technology they want, because they just speak over HTTP. But this flexibility comes at a cost, And first and foremost, building the HTTP request is way more tedious than just calling a function. Also, if you want to expose a public-facing API, documenting the HTTP requires a lot of effort, and you have to keep it updated with the server implementation. So that's a lot of maintenance work. It's also untyped, so you have no compilation assistance to check that your requests are correctly formed. No tooling assistance. And I think this is it for the limitations. So, but we have invented better solutions, right? And there was a solution invented 20 years ago about these very problems of having no tooling assistance, right? And building HTTP requests. And the solution I'm thinking about is WSDL. So with WSDL, you have a description of your API, and then you have tools that will generate a client in the programming language of your choice, so that you have a nice, more practical to use API to invoke the service. And in Scala, we have scala-XB, for instance, which does just that. And with scala-XB, you just invoke a method on an object, and this invokes the code generated by scala-XB that will actually build the proper HTTP request and decode the responses. So WSDL is nice, but it has some problems as well, right? So, for instance, it does not support streaming, so it was invented ages ago. Also, service definitions are hard to maintain, and most importantly, I think it relies on code generation, and I think this is the most important limitation. So why is that a problem? So first, it requires you to set up a new step in your build, so that when you change something in the service definition, you automatically regenerate the client that you use in your application. Sometimes the generated code does not compile, so you have to just try things in the service definitions to make it compile, but you have no idea of what is the reason for the generated code to not compile, because the error is reported on the generated code, not on the code of the service definition. And sometimes the code that is generated is not practical to use, and you have to implement an additional layer on top of it. And finally, in general, solutions that rely on code generation offer a source language that has poor means of expression, which means that you can hardly reuse parts of your API endpoints at several places in case they are repeated, or you cannot write a function that returns, that computes some parts of the API based on some, I don't know, configuration parameter or any kind of input parameter. So that makes these source files very hard to maintain over time. But WSDL was invented ages ago. So what is the current replacement to WSDL today? Yes, gRPC. And which is, I think, the best evolution of WSDL. So now service definitions are human readable. It's just plain text files that are easy to read and write, and that can just be shipped as documentation. So this is great. It has great performance. It supports streaming, but still, it relies on code generation. The last type of approaches I want to mention are those based on metaprogramming, and I think these approaches tries to minimize the drawbacks of code generation by synthesizing code by the compiler instead of using a tool to generate code. And so the programming model typically looks like the following. You have to define a Scala trait, for instance, that describes the interface of the service you want, the remote service you want to invoke, and then you can ask the compiler to synthesize a client for this service. And once you have done that, you have an object. We don't know what is the type of this object because it has been synthesized by the compiler, but you can invoke the compute operation on it, and it will return you a feature of the result because it's a remote invocation, right? So this is typically the programming model you have. And in my opinion, the limitations of this approach is that it has poor tooling support in general, because in general, tools know the semantics of the Scala language, but as soon as a macro is expanded, then you just introduce new semantics to the language that the tool is not aware of, so it cannot support it. And also, it's a second-class citizen solution, because the input of the macro has to be a static fragment of Scala code. So it cannot contain data that comes from some input, from some configuration file, for instance, or something that you read at runtime. So it is also a bit limited in terms of expressive power. So I've tried to give an overview of various approaches, and when I've used them, I've never been very satisfied of them, so that's why I've been exploring a different approach based on a library, and I will show you how it looks like. So no, not that one. That one. Am I still sharing my screen? Okay, yes, okay. So this is a Scala project. We have a server module, a client module, and a shared module that can contain sources shared by the client and the server. And the server, I will just start it. And the server is just an Akka HTTP server, which currently serves one HTML page that just contains a simple HTML form. So let's have a look at what it shows. So we can see this web page, and I will show the network activity here. Okay, and so we have a simple form, and I want to say hello to scala-italy, and I have this button, and when I click on this button, nothing happens. So let's go to the code. So when I click on the button, this function is invoked, but this function is empty currently. Okay, so there is a small lag. And so what I want to do is to define an HTTP endpoint that will be invoked by the client and that will be handled by the server, right? So before I can invoke the endpoint, I must first define a description of it. So that's what I'm going to do now. So I've created a trait which extends algebra.endpoints, and I now inherit from operations that I can use to describe endpoints, HTTP endpoints. So this is how it looks like, for instance. So here I've defined an HTTP endpoint, that uses the verb get and the URL /hello, and that returns as a response plain text response, right? So what I want to do is to take as parameter the name of the person or the Scala conference I want to say hello to. So I will just add a query string parameter. And so this query string parameter has type string and has a name, which is name. And so this is a description, and this description is just a Scala value, so I can just name it, right? Up. And it's a value that has a type, so I can just see the type of my endpoint description. I can see that it has type endpoint string string, so the first string corresponds to the information that is in the request. So here that's the name parameter, and the second string corresponds to the information that is in the response. So now that I have defined this endpoint, I can, this definition is just a description of the endpoint, and now I want to interpret this description from the point of view of a client, so such that I can invoke the endpoint and effectively build a request. So I will do that in the greeting client. So what I did is that I extended the trait that provides me the description of the endpoint, and then I have mixed an interpreter that gives the description a semantics of a client. So now, when I reuse the, oops, no, not that one. When I reuse this hello value that I have just defined in the greeting file, so this is the very same value, I can just use my ID features to navigate in the code. So now this hello value is a client for the hello endpoint, and I can invoke the endpoint as a function. So I just need to supply a parameter and to build a request, and I will get a response. And again, my ID can tell me what is the type of the result, so it's string. And now I can, so it will take a bit of time, but I can just update the type, the web page to show the response. And so in case of error, we show an error in the console, and in case of success, we update the page. So here I'm just writing something into an empty HTML element that will show the response of the server, right? So I've just implemented the invocation of the endpoint. Now I'm recompiling the project, and I will see what happens if I click again on the button. So is it starting for real or not? It's still recompiling, so I will just wait a few more. Okay, seems to be okay. So I will just reload the client. And now, if I click on the button, I can see that a request has been constructed and has been sent to the server. And of course, I get a 404 response because the endpoint is not implemented on the server. And I can see the error message in the console, right? Okay, so let's move on. And in order to fix this problem, I just need to implement the server side. Okay, so I will just follow the same approach. I will extend the greeting trait that describes the endpoint, and I will mix an interpreter that will give a server semantics. So now I can still refer to my hello value, but I need to provide the business logic, right? So I need to say how I turn the data that was in the request, the string data that was in the request, how I can turn it into the string response. So this is the straight logic, and so in my case, you can see here that I've mixed an interpreter that uses aka-HTTP. So what I get when I provide this implementation here is an aka-HTTP route. Oops. And I can just add this route to my main HTTP handler, right? And now, if the server has restarted, it seems to have restarted. If I try again to send a request, I should get 200. And so I got a response, and the content of the response is shown in the web page, right? So the server has handled the request and has constructed a response, and the response has been decoded by the client, right? So this is basically the programming model. Another thing that I can show you is that what happens if my endpoint evolves, and not only I want to say hello to the name of the conference, but I also want to have like the number of attendees of the conference. So I can just add a new parameter to my endpoint. And now, of course, if I try to compile this, it will not work because the request now takes string and int, right? And now if I try to compile this, then the client will fail with a compilation error, right? Because I'm supplying a string, but the endpoint expects a string and an int, right? So I think you got the idea. And another thing that I will not have time to show is that we can, so I've shown how we can get a client, a server from the description, and another thing we can get is a Swagger description of the API so that we can publish the documentation of the API, right? But I will stop the demo here and go back to the slides. And I will now summarize the main design decisions I've made. So the first one is that it is implemented just as a pure Scala library, and this is a very personal preference. I really like the idea of being able to address any kind of domain-specific problem with a library implemented on top of a very domain-agnostic programming language. And I think it has great benefits because you can just reuse the programming language that you are used to, and everything that you are, all the tools that you are used to work with just work as well. Yeah, and as you have seen in the demo, the endpoint descriptions are just plain Scala values, so you can just do whatever you are used to do with values. Like for instance, that part, I think that line is too long. So if I want, I can just just extract things as a separate value. And so I can just use the code editing feature that I'm used to. I can write function that return an endpoint description based on some parameter in case I have several endpoints that follow a common pattern. I don't use any macros, so there is no surprising semantics. It's mostly IDE friendly. And another thing that I've shown is that it's modular. So from the same description, you can get very different specific interpreters. Like I've shown the AKHTTP server. I've shown the Scala.js interpreter client. And then if you work with JSON, you can use Cersei on on the backend, for instance, and play JSON on the front end. Whatever. There is no coupling between those parties because at the level of the description of the endpoint, no choice has been made about the underlying technologies that will be used. So that's one level of modularity. But there is another dimension of modularity in that the language that we use to describe the endpoints is modular as well. I've just shown how to use the endpoint description language. But in case you need more capabilities, for instance, if you want to work with JSON, then you can just add the optional JSON schema module to your description language. And it is optional for a good reason, because there are several ways to work with JSON. For instance, I can just give two examples. One way to work with JSON, in case you want to document your API, in that case, you want to publish a schema of your JSON entities, and that's what will be required by this module. Another way to work with JSON, in case you don't publish your documentation, you don't care about a schema. You don't want a schema. You just want, for instance, to use a codex automatically generated by Cersei, for instance. And in that case, you will not use the JSON schemas optional module. You will use another one, and you won't have to provide the schema. You don't care about it. And that's the same for streaming. It's optional because not all the underlying backend, client or server have the same streaming capabilities. Not all the clients support WebSockets, for instance. So it's optional. And because of this modularity in two axes, you get extensibility, which means that if you have an application-specific concern, like authentication, you can just extend the description language with your own operations to describe the authentication, and then you can just implement your own fragment of interpreter that can reuse an existing interpreter to support the authentication capability. So this gives you a lot of flexibility at the cost of some complexity, I agree, but I think it's nice to provide this level of flexibility for advanced use cases. I'm done. Thank you. Do we have time for questions? Are there any questions anyway? Yes, one question.
Yeah. So the question is, when you generate a client, how the client know where is the server? I didn't see you passing the host of the server, so I'm wondering how this is being done.
Right. So it depends on how you compute the client. The Scala.js client that I've shown you expects the server to be on the same host as the client, but other interpreters take the host as a parameter. So for instance here, you would just specify as a parameter the host of the server, right? As a parameter of the constructor.
Yeah, okay. And then have you foreseen or is on the plans to have something that's not a host but a name? Because sometimes if I'm deploying my application in Kubernetes, I don't know the IP, and then I need to identify it by a name. So basically, service discovery.
Yeah.
You're
That's
also,
something
yeah.
possible. Yeah.
It's possible, or it's already in there, or it's something that you plan to introduce?
No, it's something you can do. I just need to check, but
Yeah.
I mean, this is just a parameter that we supply
Yeah.
to the client. So
Yeah.
I just need to check if it works in that case as well.
Yeah, it's pretty much similar to DNS.
Yeah.
Basically, you give a name and. Okay, thank you.
Mhm. Any other question?
Would it work with refined types and the documentation generation? Would it work with refined, for example?
That's a good question. Yes, we could do something that would provide like documentation based. We could have a refined module that would provide documentation based on the existing types provided by the refined library. Yeah, but there is nothing like that currently.
More questions? I'm just curious, how do you compare using that library with using GraphQL for client-server communication?
I think that's a bit orthogonal. Yeah. Because GraphQL is just like a way to build a request on your backend to fetch the data requested by the client. So the responsibility of that library, if it was used in a GraphQL environment, would just to decode the client request and then forward the part that computes the GraphQL query to Sangria, for instance, and then return the response to the client. Does that answer your question? Yeah. Okay. Great.
Any more questions? Okay. Thank you, Julien.
Thank you.